Okay, let's see. Great, I think we can start. It's a pleasure for me to introduce today's speaker, Brian Swingle. He comes from Brandeis, where he's a newest faculty. Brian got his PhD at MIT and then spent time at Harvard, Brandeis, Stanford, and before coming to Brandeis, it was Maryland. But I recall early on that he contributed very significant papers to some of the subjects that he will be talking about. At one point, I think his affiliation was MIT, Harvard, and Brandeis together.
That's right.
Caught my eye. But from early on, the important contribution to theoretical subject of entanglement, renormalization, and holography. That was a relationship which Brian contributed a lot. He was very instrumental in bridging two very big subjects, information science and quantum field theory, with notions of complexity and relating that to properties of black holes. One of the very interesting recent papers, which will catch your eye also, is our two papers entitled Quantum Gravity in the Lab. That's something we all want to read about and understand. So today's subject is on quantum chaos, from hydrodynamics to renormalization to random matrices. That is a big field to which Brian contributed a lot. So with that, I'm very happy to announce his talk.
Great. Thanks a lot, Antal. That's a very kind introduction. Thank you all for being here. Thanks for having me. It's a pleasure to see people in person. Greetings to all you Zoom folks out there as well. It's nice to be sharing the same virtual space as you. And yeah, today I'd like to tell you about the subject of quantum chaos and how that subject has been evolving significantly over the last, say, 5 or 10 years. And that evolution has really brought together a lot of different threads in theoretical and experimental physics, from condensed matter physics to quantum gravity to quantum simulation and AMO systems. And so for that reason, it's a very exciting time to be thinking about this physics, I think. And I want to just try to give you a little bit of a flavor of the topics we're thinking about, and also, because I'm a theorist, some of the theoretical tools that we're bringing to bear on this problem. Okay. And you'll see we're going to kind of try to take a journey from sort of hydrodynamics to random matrix theory and see how these things are all related to each other. Okay. So I want to start with the puzzle of irreversibility. This puzzle is as follows. Quantum systems, of which we have many in nature, display all the time seemingly irreversible behavior. This can be something as simple as dissipative transport, so diffusion, which generates heat, resistance, the relaxation of thermal equilibrium, and even something as exotic as the apparent loss of information in black holes can be regarded as an example of this kind of emergent irreversibility. But we all know that, or at least we learned once we've taken sufficient quantum classes, that according to our best understanding, the Schrödinger equation, which underlies all of this physics, is time reversible, right? It's just unitary evolution, probability is conserved, no information is ever really lost. And this is not just a sort of esoteric theoretical question. People have been thinking about experiments in this area for a long time, going back at least to the work of Hahn in the 50s, where he studied spin echoes, where you take a bunch of spins in a nuclei, and these spins start out aligned and then they become unaligned after some time, but he showed that by applying the right kind of coherent control, you could make them magically realign. And that's the echo. And what we're going to do later in this talk is talk about many body versions of that echo and how we can probe that in the lab. Okay, so that's the basic setting, but you may say, so what? I know the answer to this question. Any quantum system is always coupled to a big bath. And doesn't that address the issue of irreversibility? Right, I'm always radiating infrared radiation out into space, and space is very large, so on any practical time scale, I'll never come to equilibrium. And so maybe that can explain everything that we see. I think that's not the full story, even from a purely theoretical point of view. For example, if you include the environment, however big it is, in your description, you have the same problem again. And you also have to understand how subsystems of that big system can look like they're in equilibrium. But maybe even more directly, thanks to really rapid developments in experimental physics, we're actually able to construct and probe on long time scales compared to the microscopic scales, really effectively isolated quantum many-body systems. So we can build these in the lab and we can study them for time scales long compared to the basic time before the environmental effects take over. And we look at those systems, and lo and behold, what we see is they still exhibit irreversibility. Okay. So it's really an intrinsic quantum phenomenon, even if you don't have this big bath there to help you out. And as I'll also try to convince you, even if this bath is always present, it's conceptually very useful to think through how this irreversibility could emerge in an isolated system. That tells us a lot about a variety of interesting and tough subjects that we'd like to understand still today. What are some of those subjects? Well, on the top, I started out life as a condensed matter theorist. And so one of the things that we like very much in that world is to measure transport, the motion of electricity, and also energy, but especially electricity. And here's a standard phase diagram in the field for a material called a high-temperature superconductor. And I won't explain in any detail what's going on. This is just flavor text, basically. But what's shown here are ρ, which is electrical resistivity, and its relationship to temperature. So in these different regimes, you have different relationships between resistivity and temperature. And we'd really, really, really like to be able to calculate microscopically what's going on in all these different regions. But even if we know the underlying quantum mechanical model, if we have a good approximation for it, we still typically can't calculate this. So it's a very hard problem in theoretical condensed matter physics to determine these resistivities. And I'll try to convince you later in the talk that thinking about chaos can help us understand how to calculate these quantities. Right? So that's an extremely practical, everyday kind of experiment that you might gain insight into from thinking about quantum chaos. Now, another slightly more exotic or out there connection is black holes. Here I'm showing actual data from LIGO where they saw this merger. And you can see that there's kind of there's some growing oscillations or wiggles. And then beyond this point here, the wiggles start to die away. That's the ring down to a final state where the black hole has settled into a sort of equilibrium configuration. That ring down is called a quasi-neural mode. And it's the same kind of decay, roughly speaking, as you see in, say, condensed matter systems when we excite them and they relax back to equilibrium. And then sort of more theoretically, the existence of the event horizon, through which seems like a unidirectional membrane, through which information can only pass one way, gives rise to the famous information problem of black holes. And so the irreversibility is there too, and it's really a very fundamental aspect of quantum gravity that we'd like to understand to give us clues into that theory. Because we don't have experimental access to the quantum physics of space-time yet, at least not very directly. But we can, by thinking through these theoretical questions, hope to gain insight into that problem. Okay. Now, what I want to claim in this talk is that these different things of irreversibility are all avatars of what I'll call quantum chaos. And so what is quantum chaos? Well, this is a very interesting history. I think, I'm no historian, but my impression is that in the early days, quantum chaos was about the sort of semi-classical physics of classically chaotic systems. So you take a system that's classically chaotic, you quantize it, and you ask, what are the signatures of that classical chaos in that quantum system? And there were also arguments sometimes made that, okay, the Schrodinger equation is a linear equation, and so it can't have chaos in any kind of fundamental sense. And that's true. The wave function does not have exponential divergence. But if you think a little bit more about it, you might say, well, chaos is really about observables, the motion of observables. Saying that the Schrodinger equation is linear is like saying that the Liouville equation is linear. That's true, but it doesn't mean you can't have classical chaos. So what we really grew to want in this field, from my perspective, is a kind of fully quantum notion of chaos. What we should mean in a quantum mechanical system where there may not be any semi-classical limit. What should we mean by chaos in that kind of system? And certainly we should recover the classical notions in the regime where they are appropriate. That's why we call it quantum chaos. But there's all these other different manifestations or avatars that appear, and we'd like to understand how they're related. Are they really fundamentally the same thing, or other different flavors of quantum chaos? What's going on? So these avatars are things like the scrambling of information, eigenstate thermalization, I won't define that, the growth of complexity, also the idea that you thermalize or have transport, hydrodynamic transport, and then a specific very famous one is what's called random matrix-like energy level statistics. And I'll explain what these things are in a second, but just to give you a kind of big picture, there's all these different bubbles here containing, you pick your favorite model, you look at these different pieces of physics in that model, you'll find that they all say, okay, it's chaotic, but do you really know that for a big class of systems, they're all related, right? And again, the reason why we care about this, apart from just wanting a fundamental framework for quantum chaos, is precisely because it can help us understand some of those hard problems in quantum gravity, for example, or in strongly correlated electron physics, and in a variety of other contexts. So what I'll describe today is a sort of trajectory. Well, I'll first explain to you what is information scrambling at a very high level. Then I'll show how that relates to thermalization. And then from that, I'll show you how you can get this random matrix structure out. So I'm going to tell you kind of a path through this garden of chaos. And of course, you can try to have a lot of other paths that are interesting to follow, but I'll take this particular one today for this talk. Okay. So let's look in a little more detail what these different physical properties are. What's the idea of information scrambling? Well, it's like you're sitting around a campfire, you write a note on a piece of paper, you throw it into the campfire, and then it gets burnt up. Now, in the same way that we think, Schrodinger equation's reversible, Newton's laws are reversible, well, the information is still somewhere in the ashes and smoke from that fire, but you basically can't figure out what was written on that piece of paper. For all practical purposes, it's lost. You would essentially need a device that can perform some very subtle correlation or study some very subtle measurement on all the ashes and all the smoke, which probably would amount to just reversing time effectively for that set of things to figure out what the information was. Now, this is a kind of classical version of information scrambling, information hiding, but it also happens in quantum systems. So here I'm showing you a theorist's version of one of my favorite chaotic quantum systems. This is a chain of interacting spin-a-halves. So imagine you have electrons arranged in a line. They sit at discrete points on this line. And their motion is frozen, so they're not moving anywhere. But their spin degree of freedom is still active, right? And this Hamiltonian, this energy function, describes a set of interactions where the spins prefer to align in the z direction. That's what this first term says. But they're also subject to magnetic fields in the x and z direction. And take it from me, this Hamiltonian with generic parameters is quantum chaotic. And I'll show you what I mean by that. Here's two initial states. State 1, all the spins are plus in the y basis, so they're just starting polarized in the y direction. And state 2, all but the first spin is polarized in the plus y, the second spin is polarized in minus y. So these are two quantum states. They're perfectly distinguishable from each other. You just need to measure the first spin, and if it's plus y or minus y, you determine which state you have. And we can evolve them under time and see what happens. And I can do this calculation on my computer. I could even do it on this computer, as long as there's not too many of these spins. I can simulate what an experiment would actually see. There are experiments that study this kind of thing, but I'm not going to talk about that yet. And this is what you would see if you did that experiment. On the x-axis, I'm plotting time in units of the nearest neighbor interaction. And on the y-axis, I'm plotting the expected value, the average value of the measurement of the spin, the y spin on the first site. And what you see is that at time 0, they're perfectly distinguishable. One is plus 1, the other one is minus 1. Plus h bar over 2 or minus h bar over 2 if you restore the units. And there's oscillations and wiggles as a function of time, but after a relatively short time, after about, say, 6 or 8 time units, the two curves look almost indistinguishable. In fact, if I covered up the first part of the graph, you'd have a hard time telling me which one was up and which one was down. Right? And moreover, they're oscillating around 0, which is exactly the value you would predict in thermal equilibrium at that energy density. So it looks as if the system has gone to an equilibrated sort of configuration, and it can't tell which of these two states it started in, at least as far as this simple measurement is concerned, right? And now I claim, and I'm happy to give you the code, you can check yourself, you can measure spin on any other site or combinations of spins, so whatever you do, you'll all see the same kind of flat, indistinguishable structure. Yes?
In your initial setup, I don't see temperature anywhere, so where did this thermalization come from?
Well, yeah, so it's thermalizing, but I didn't say to what. But if you go back to this situation, I chose this state somewhat sneakily so that the expected value of the energy is 0 for both of them. And that, for this Hamiltonian, is right in the middle of the spectrum. So if you go to your thermodynamics or your stat mech class and you ask what should be the temperature of this state, it should be infinite temperature. So it should converge to a maximally mixed density matrix. And infinite temperature makes sense for this model because it doesn't have like particles moving around. It just has a finite set of states. So it makes perfectly good sense, and it just means it converges to a state that has no structure at all. Everything has 0 expectation value in that state. Right? So thermalization means it converges to the thermal state whose temperature is such that the energy would be equal to the initial energy of the state. Because energy is conserved, so we never change that, and whatever we get to at late time has to be the same as that.
So you assume partition at the very beginning.
Well, I'm just telling you what the prediction, if you like open your StatMech textbook and apply it to this problem, it would tell you that you'd go to a certain infinite temperature state, and then I just run the simulation, and that's what you get. Like the observables here are completely consistent with that state. So that's all I mean. I'm not making any more complicated statement than that. Just that the simple observables you would measure in your imaginary experiment are consistent with this thermal equilibrium state, up to these small wiggles here. Okay, so that's what happens after a short time. You can go to longer time on your computer at least. It's hard to do experiments for this long of time, but at least without having the environment. But you can go to longer time, and what you see is that they both just stay right around 0. There's all kinds of random looking wiggles, but apart from that, you just stay in this equilibrated state for a very long time. In fact, you can go and ask, just for fun, how long would it take for the system to come back to its initial state? And I asked my computer to calculate that for some small size systems, up to 2, 3, 4, 5 spins. Beyond that, I couldn't run the computer long enough. And so here is system size, and here is the logarithm of the time it takes to come back. And it's sort of roughly straight. So this means if you have 100 spins, it takes 2 to the 2 to the 100 units of time to come back. Now, if you think about that number, it's a very, very big number. It's like a lot bigger than the age of the universe. So for any practical purpose, even forgetting about environmental effects, we can ignore the state coming back to itself, right? So system will equilibrate, and it just stays there for as long as you can possibly imagine waiting. That's a Poincare recurrence, yeah. The quantum Poincare recurrence. Okay, so that's scrambling. You see how the initial information about which state you were in gets mixed up and lost and stays lost for a long time. But this system also has more conventional kinds of physics. For example, it has diffusion of energy. If you take that chain and you place a hot bath at one end and a cold bath at the other, and you bias it so you have different temperatures, then energy current will flow, energy will flow, heat will flow, and it flows diffusively. It obeys Fick's law. And as I'll explain to you later, we can actually calculate the energy diffusion constant of that system precisely because we can use these chaotic ideas that I'll describe to you to help us kind of get a handle on the dynamics of this system. Prior to this kind of work, no one on Earth knew how to calculate what the energy diffusion constant of this was. Believe it or not, a model as simple as that, no one knew how to compute it. It's just not known. But we think we know how now by using these ideas of quantum chaos and also other quantum information ideas. Now, the final thing I'll mention before getting into a little bit more detail is random matrix energy levels. So here's that same Hamiltonian, my favorite Hamiltonian, with 8 spins. And each spin can be up or down. So there's, you do the math, 256 different possible configurations. And here in this kind of barcode, I've just plotted the energies of those different configurations just as a function of energy. And there's a special state down here. That's the lowest energy state, or the ground state. There's also some relatively special states up there at the top. But most of the states live in the center here. You see near zero energy, which is the infinite temperature I talked about earlier. Most of the states live here, and it's just by eye at least, a more or less featureless, jumbled mess of lines, right? There's not a lot of structure there. And that can be codified in the idea, going back to Wigner, and really made into a solid conjecture in the quantum chaos literature by Bohigas, Johnny Schmidt, that the eigenvalues, the energy levels of this Hamiltonian, are in a certain precise sense like those of a random matrix. So you just take that Hamiltonian, which is a big matrix, right? You remove all the levels, put in random numbers in that matrix, and in a certain precise sense, the claim is that the spectrum looks statistically the same as if you had this physical system, right? And this is very universal. So whatever your favorite quantum chaotic system is, it should have this feature that its energy levels look random matrix-like. So that's three different things that different people in different communities refer to as quantum chaos. And I'd like to now show you how we can relate those things and try to move towards a picture where we have just one kind of quantum chaos, one overarching framework with these different manifestations. Okay, so that's where we're going. Yes?
Is there a map between, like a mathematical map between two models, or is it just not as straightforward?
No, it's like you can take any value, well, more or less any value of j, h, x, h, z. You need to add a little bit of randomness so we have an ensemble. And then whatever you choose, in a certain sense, it will look like the eigenvalues of a random matrix. And I'll define precisely in what sense in a little bit. So it's a very striking, like it doesn't care whether your system is in 1 dimension or 2 dimensions or 3 dimensions, whether it has long range or short range, all to all, fermions, bosons, spins, whatever. It seems to work, right? So that's an extremely striking universality that you can actually see in nuclear physics. You can look at lifetimes of decays, and they obey laws, statistical laws predicted by random matrix theory. And we like to understand that universality. Okay, so let's talk about scrambling now. Let's go back to our thought experiment. We had the two initially distinguishable states, and ask, if we evolve for a while, how do we connect those two states? How do we turn one into the other? And one way you can do it, the simplest, conceptually simplest way, if you imagine you have complete control over your system, is that you can evolve the state backwards in time. So undo the evolution, apply the operator which flips the spin from plus to minus or vice versa, and then go forward in time again. So that's the process where you say, do some evolution, you do a perturbation, then you try to reverse the evolution. And if you think about it for a second, this is like a kind of different version of the butterfly effect thought experiment in classical chaos. That thought experiment says you take two nearby points and you watch them evolve under time, and they initially kind of stay close together, but then after a while they spread out and diverge exponentially fast. That's the classical butterfly effect. And an equivalent version of that would be you take one point, you go forward in time, you make a small kick, and then you go backwards. And if you didn't make the kick, you get back to exactly the same place you started from. But if you do make the kick, then eventually you get somewhere else quite different. And rather remarkably, this operation, which is in quantum mechanics called the Heisenberg operator version of the perturbation W, which was just in quantum mechanics class just some mathematical construction you do to describe time evolution. Here it very naturally mimics that butterfly effect thought experiment, where you go forward or go backwards, it doesn't really matter. Go forward, perturb, then try to rewind, and see that you end up somewhere quite different. So let me show you how this works for, again, my favorite model. Here's a bunch of interacting spins. I call them qubits here for quantum information, but let's just think of them as spins. They're arranged in space along this line, and time runs up. So each of these black lines is like a world line of one of my spins. And I will think of time evolution as a series of interactions between neighboring spins. Right? Just a mathematical fact that I can always take that Hamiltonian I wrote you before and think of it as a bunch of blocks like this. The details are not really important, but you can always think of it as blocks. You can think of these blocks as being like containing the J interaction between the neighbors, as well as part of the field that rotates each of the different spins. So that's the forward evolution. That's the backward evolution. And if I go forward and then go backwards, because quantum mechanics is unitary, what happens is they cancel, U and U dagger, and I get something which is equivalent to doing nothing. Right? But now suppose I throw into the mix my butterfly, my fly in the ointment, which is going to perturb just one spin. So I'm just flipping the quantum state of a single degree of freedom. A butterfly's wing flap, by contrast, is a very dramatic thing, which involves the motion of lots of atoms. Right? So here I'm just taking a single electron and changing its spin from up to down. What happens? Well, I try to do the same cancellation procedure I did before. And now, in the first step, most of the gates will cancel, most of the interactions will cancel, but some of them that touch the perturbation will fail to cancel. But that I just mean that they don't exactly give you identity, they give you some more complicated operation, effective operation, which now lives on 2 lines instead of just 1 line. So now it affects 2 qubits instead of just 1 qubit. So I'm going to color it blue to indicate that the perturbation has spread a little bit. And now I do the same thing. I try to cancel again, and the perturbation spreads a bit more. And I keep canceling. The perturbation spreads a bit more. Keep canceling. And you can see it looks like what I have here is an emergent light cone, some kind of propagation, ballistic propagation of the perturbation, which was initially located on a single spin, over time begins to affect a large number of spins in a fashion that grows ballistically with time. And this is just some jargon in case you're interested in what these things are. You may have heard about them in the popular press. One way we like to probe this growth of perturbations is to look at commutators. And you can think of this as saying that W of t is the growing thing, V is like a probe, and I'm asking, does the probe commute with, meaning can I do the probe before or after without consequence, this growing thing? And so if the probe kind of overlaps with the blue structure, then they won't commute. And if the probe is far away, then it will commute. And that's a way of sort of testing theoretically how big this structure has got. And if you calculate the square of this and compute its average, that's something called an out-of-time order correlator, if you've ever heard about that. I won't talk in more detail about that, but that's the jargon. The important thing for me is that apart from being theoretically useful, this is something you can actually measure in an experiment, rather surprisingly. In fact, we need to go back to our friends who study nuclear magnetic resonance. It turns out, using something called magic echo technique, which was developed in the 70s, that people in that community have been measuring this quantity for almost 50 years, or a certain version of it, or a cousin of it. And in that context, what you can do actually is measure not the OTOCs, the out-of-time order correlators of these local operators, but of global things. So you add up all the spins, and you ask how one sum of all the spins fails to commute with another one. And very recently, in a paper that hasn't appeared yet but will appear soon, a postdoc, Tianqi Zhao, and I showed how to relate actually that observable that people in NMR measure all the time under the name multiple quantum coherence to the kind of things that we like to calculate in the quantum chaos community. And the answer is very simple. You take this OTOC, which is a function of space and time, and you simply compute the area under it. The area under the curve is what you measure in NMR. And on the right here, I'm showing you actual data, these colored dots from this paper shared with the permission of the authors, and a fit to that data with a certain kind of stochastic model that we developed is a 2-parameter fit. So I'm not claiming that we can definitely explain exactly what they see. But the point is this fit, the time scale is all we're really fitting, and it's roughly what you would expect from the actual material physics of a material called adamantane, which I show here. And the point is that this OTOC, which is like the size of the growing operator, in this experiment got up to about 120. So they're actually sort of seeing very literally in this experiment 100 plus spins in the footprint of this growing butterfly perturbation. And there are other experiments that can get up to as many as 10 to the 4 spins in this kind of growing cluster. And so this physics is really very real. It's something you can measure in experiment. And we see that, as far as we can tell, this growth just continues in an unbounded way till the system size is reached. Okay. So I'm happy to answer more questions about this afterwards, but for now, I'll just flash that up there. And then I want to move on to ask what information scrambling has to do with hydrodynamics, which was the second thing I talked about. And here the idea is, again, we can use this picture of growing operators to understand the physics of the system. We can say, well, this growing perturbation, the growing butterfly wing flap, which I call W, just like you can in quantum mechanics expand a quantum state in a basis of states, you can also expand operators in a basis of operators. It's just a mathematical fact. And this basis has some form here. And the idea is just that there are many more complicated operators than simple operators. There are many more operators that have lots of terms in their expansion than a small number of terms. And so this flow of information from simple to complex, from simple to hidden, from simple to equilibrated, can be thought of as a kind of flow of simple operators to complicated operators. And when I say complicated, what I mean is it's something that you would have to measure, 100 spins simultaneously in some complicated, coherent way to see the correlation inherent in this operation. Yeah.
At this stage of the talk, the first thing I'm thinking about is it smells like an instability. So a growing operator, right? It smells like some sort of instability. So what will make you distinguish an instability from a bona fide, say, chaotic, I guess?
Yeah, that's a good question. And there are, like, you can just think about an inverted oscillator, for example, which would have a sort of similar kind of physics. So I would say the answer to that, it's actually something the field still struggles with right now, like how to distinguish these different notions. But there are various statistical ways of telling, like this operator, in addition to just being very complicated, is like sort of looks random in a certain precise sense and has other characteristic features that we can use theoretically at least to tell them apart. But experimentally, it's less clear. Like from what I showed you on that previous slide, it's not 100% clear that that corresponds to chaotic growth. We don't really actually know what the dipole interaction in 3D. I mean, I presume it's chaotic, but nobody really knows. So this is an open question. Okay, so we have this picture of simple things becoming complicated. And we have the picture that complicated things are hard to measure. So why don't we just ignore them, right? They don't have any discernible effect on the physics. Like we saw from the previous graph, that if you look at simple observables, then they don't look different from each other anymore. Right? But there is one special exception, which is conserved quantities. Right? Conserved quantities, precisely because the Hamiltonian doesn't change them, have a special protected status. So for an example of such a thing is the density of energy. Right? If you sum up all those densities, you get the total energy, which is conserved. And that implies that the densities, the way they evolve in time, has to be restricted somehow. Because you can't just lose energy here and create it over there. It has to move from here to there. That leads to a hypothesis which says, well, if we think about the energy density as an operation, as an operator, we can think of it as some kind of protected special part, which I'll call the hydrodynamic part, and a complicated part, which I'll call the complex part. And we might say, well, whatever this complex part is, it's there, but it has unobservable effects. And so if we can ignore this part in some sense, then maybe we can calculate. Maybe we can understand how hydrodynamics emerges via this motion of operators. Now here I'll just give you a flavor of how we can use this to our advantage. Here's the same kind of setup I showed you before, where you have a hot reservoir and a cold reservoir and a chain between them. And you could imagine modeling the dynamics of energy flow in this system using what's called an open system equation. So this is like the version of the Schrodinger equation where you have a system coupled to a bath, right? So the bath only couples at the edges, the left and the right. And here it injects energy and here it removes energy. Energy flows from the left to the right down this chain. And the idea of this approach is we want to calculate the diffusion constant state. We observe that this energy current obeys fixed law, so we'd like to calculate the coefficient in that law, which relates the energy current to the gradient of energy. And we can't, as I claimed before, I didn't explain this, but I just claimed that we can't really calculate in detail how that works. It's beyond our capability. I can put this on my computer, but I can only study, say, 12, 14, maybe 20 spins, and that's not enough to see the long-distance behavior that's inherent in these transport physics. But what I could try to do is make an approximation. I can make an approximation where I say, let me throw away the complicated stuff, just keep the simple stuff, which I know how to do, right? Throw away the complicated operators. Maybe I can approximate the time-evolving state in terms of some simpler network structure. And if these nodes in this network are complicated enough, then I can represent any possible state. But if I'm interested in being computationally effective, I need to keep them simple. But maybe because of chaos, I can get away with that. Maybe because I have this flow of information from simple to complicated, which doesn't affect the simple physics anymore, I can get away with approximating the state in some simple kind of way. So we can do this calculation. A PhD student at MIT, Chris Zanocchi, and I worked on this. We wrote a paper where we studied, again, my favorite Hamiltonian, but with different parameters. And here we compute using that method I just outlined for you as a function of the gap divided by temperature, the diffusion constant. So this model, if you look, I show you that picture of the ground of this energy spectrum before. You saw there was a big white space between the lowest state and the second state. That's the energy gap. And if you go to very low temperature, the prediction is pretty simple, actually. You can get it just with kinetic theory. What you would predict is that there is a dilute set of excitations, because there's a gap to these excited states. So it's like a Arrhenius activated set of degrees of freedom. And you can do a little calculation, a fun little exercise. In 1D, energy conservation, momentum conservation imply that you can't relax energy current with two-body collisions. If you just collide two particles, it doesn't change the energy current. So what you actually need are three-body collisions. And the amplitude for such a collision should be proportional to the density squared, or 1 over that. And that's exactly what's predicted here. So this is e to the 2 delta over t. That's 1 over the density squared. And kinetic theory just predicts that the diffusion constant should go like that thing. Now, this is the actual numerical data. This blue line is that prediction with no fitting parameters. We take the gap from numerics, so we take the temperature from numerics, and it just agrees perfectly with this curve. So the point here is not that this is a particularly exciting system. It's just more or less dilute classical particles scattering off of each other. That's not super interesting from the point of view of quantum gravity or anything like that, or the mysteries of transport in high-temperature superconductors. But the point is that we have this theoretically principled way to make the calculation, and it agrees in this case with something that we can derive in a different way. Right. So we have good reason to think that we understand how to do the calculation now. And the way that we did it came from thinking about the physics of chaos in these systems. Right. And this is just one model, but now you can try to take whatever your favorite model is. So far, mostly we can do 1D. But we think the ideas are general, that they would apply in 2 dimensions as well, or 3 dimensions. This calculation is harder for various technical reasons. But nevertheless, we think there's a chance. And so this would be a really significant development in condensed matter physics if we could actually have guaranteed or at least principled methods for computing these kinds of quantities. Okay. So now I want to talk about the last part, which is the statistics of energy levels. And I'll first tell you how we define precisely what we mean by this. We use something called the spectral form factor. That's a complicated name. Essentially what it is it asks about the correlations between pairs of energy levels. The simplest thing you might ask about is just what the distribution of energy levels looks like. That's the simplest question you could ask about the Hamiltonian. That turns out to be rather non-universal. So even among random matrices, you can get all kinds of different answers depending on the precise kind of random matrix you have. So that question is not a good question to ask if you're trying to see something universal. And instead, what you should look at is the so-called pair correlation. which is basically asking if you have an energy level here, what's the probability you have another energy level some distance away? All right. And for various reasons, we like to think about that in the time domain. So we Fourier transform that. We go from energy to time or frequency to time. And then what you end up getting is sort of a copy of evolution forward in time and backward in time. That's what I've shown here. This is one going forward. This is one going backwards. You get one energy from this evolution, one energy from that evolution. You take the trace, which just means summing over all initial states. So you start in some state. You ask, what's the probability to come back to yourself? You square that, and you sum over all the states. Right? This summing over all states is not crucial. It's just a sort of theoretically simple way of accessing things. This kind of forward-backward is the key part. It has the same physics as we saw in the butterfly effect there, the quantum butterfly effect. It has the same physics of that hydrodynamics in it as well. And the prediction of random matrix theory is that this spectral form factor, as a function of time, is just linear in time. That's the prediction, with a certain coefficient that you can calculate just based on the density of energy levels. And in fact, if you look at just a small window of the spectrum, it's totally universal. So there's just some 2 pi, some square roots, and the size of the energy window times time, which makes this a dimensionless quantity, and that's the answer. And you can go to that spin chain, my favorite spin chain, and compute this thing, and you'll see that it obeys this law very precisely. Okay? And you can take whatever your favorite system is, and it'll also obey this law if it's chaotic. So here's what that quantity looks like in a little bit more detail. This is a function, this spectral form factor as a function of time on a log scale, and then this form factor also on a log scale. There's some early time value which drops very rapidly. There's some wiggles. This is all happening at relatively short time. So sort of some fast stuff happens, some stuff that's not universal happens, some stuff that's system specific happens. Then after a while, that stuff dies away, and you get this very, very nice linear ramp. And if the system is large, this will continue for a very, very long time, out to a time of order exponential in the system size, at which point it will take a plateau form. So this ramp, as it's called, is one of the characteristic signatures of randomness in the spectrum. And in fact, it's often taken as the definition of quantum chaos in the field. So what does this have to do with what else I've talked about in this presentation? Well, let me start by asking, how can this apply to a physical system that has all kinds of details and particular features? For example, let's think about, again, our Hamiltonian, where energy is diffusing slowly. If you think about that, what that will tell you is that there are certain excitations of that system that decay very, very slowly, right? Because that slow dynamics is their slow motion of energy as it diffuses around the system. In particular, there's a wave vector here, such that all the energy modes with wave vector less than that characteristic value have barely decayed at all. Right? So it's actually like you have not one system, but for each of these different amplitudes, a separate system, which can interact strongly with itself. But these almost conserved modes, well, they're conserved, which means that they can't have correlations between them. Right? If modes are conserved, there can be no matrix elements in the Hamiltonian, so it can't possibly have correlations between the energy levels in these different sectors. And a simple calculation, you can estimate how many modes you have. You just count the number of wave vectors less than this characteristic wave vector. It's extensive. And so you predict that at any finite time t, you're going to have an extensive number of almost conserved quantities. And that will mean you can't have one big random matrix, but a large number of small random matrices. And you can easily show, with just a little bit of mathematics, that what that predicts is that instead of getting this ramp here, you're going to get the ramp times a big enhancement factor, which is the number of modes. Or the number of sectors, really. Okay. Here's just a way to show you how it works. Suppose you have diffusion with fluctuation. So this is the diffusion equation here. This little xi funny thing is a noise. So it's some random fluctuation. I've chosen it so that energy is conserved, of course. but this is the standard description of fluctuating diffusion. You can calculate with this equation what is the probability that given some initial amplitude of energy excitation, you return to that same amplitude after some time. Right? That's what this spectral form factor was asking of us, right? As we start in some state, we go for a while, we come back to the same state. What's the probability of that? You can do that calculation, and you predict indeed an enhancement factor, which is the exponential of roughly the number of modes that I showed you before. There's a slightly different factor, some zeta functions, etc., but you can compute all that. Then you can go to your spin chain. I'm going to unfortunately show you a different spin chain now. I won't tell you the details of it, but you can look now at numerical data. You can calculate this thing. And you can plot here as a function of time the log of that spectral form factor, that's here called k, divided by the t, the ramp. And what you see in this plot, which contains data from this paper here, numerical data, is that as a function of t over L squared, this is like the characteristic time scale of diffusion, you have data collapse. Different system sizes collapse almost onto the same curve. That's the different colored things. And then this black line through all that is that theoretical prediction from the previous slide. So the point of this is just that we understand how this thing deviates from a random matrix. It does so because there are these slow degrees of freedom. And as time goes on, that deviation dies away. Okay. So that's at least one connection between hydrodynamics and random matrix theory. It's telling you the time scale beyond which you can actually have this random matrix behavior. But the connection is actually deeper than that, as we discovered. Let me show you just very schematically how we think about this theoretically. If you want to describe hydrodynamics, it's particularly convenient to use something called the closed time path formalism. I won't explain what this is in any detail. I'll just show you a picture that kind of captures the idea. The idea is you have some initial state here, which is the purple bubble, and you go forward in time and then backwards in time. And that's just capturing the evolution of the state with the ket and the bra parts here for the density matrix. Right? And I've taken a trace, that's why I connect things at large time. And the reason why you care about this quantity is that it's like a generating function. So if you've done stat mech and you've ever computed magnetization by taking derivative with respect to magnetic field, that's all this is. This is a fancy way of computing correlations between energies using magnetic fields, so to speak, fields that couple to that energy. Right? So it's a mathematical tool, but it's a very powerful mathematical tool which has a lot of nice properties. In particular, because there's sort of a forward part and a backward part, all your fields are doubled. So there's a field 1 and a field 2, or a symmetric field and antisymmetric field, as it's more convenient to write. Yeah, this is Schwinger-Keldysh, right? And the way you can get diffusion in this case is for example, you have a Lagrangian like this, right? And what does this mean? Well, to get some understanding, imagine that you take a derivative with respect to phi a of this. So you're like computing the equation of motion in classical mechanics for this Lagrangian. And the derivative with respect to phi a just encodes the diffusion equation as its equation of motion. Right? And then there's another term here, which I won't explain in detail, but which is responsible for those fluctuations that I wrote on the previous slide. So I don't imagine that you know getting anything in detail from this slide, just to tell you that there is this mathematical formalism that we can use to calculate diffusive properties. But it has all these coefficients, d, kappa, etc., which we need to compute from some microscopic theory. But I already showed you how to do that, so we can regard that as known. And now the big insight is that if we put these two pictures side by side, the spectral form factor picture and the closed time path picture, they look almost the same except for the boundary conditions. Here we have a state and the trace. Here we just loop the future back to itself and the past back to itself on these two contours separately. So the key idea that my student Mike Weiner and I had is that you can take the theory of this object, modify the boundary conditions, and get the theory of this object. Right? And maybe that would be a sharp way of explaining how hydrodynamics constrains random matrix theory, or the emergence of random matrix theory. And we gave some sharp arguments for that, but the proof is in the pudding, as they say. The proof is the fact that it works. In fact, it works better than we thought. We thought it was just going to be a way of calculating this approach to random matrix behavior, but it works better. If you look, for example, at the zero mode of that Lagrangian, you do the path integral over that thing. You compute your statistical mechanical partition function, so to speak. What you'll find is that there's a relative time shift between this circle and that circle. You have two times, and you can correlate them in any way you like. There's a relative degree of freedom there. And that degree of freedom is exactly the linear in time factor that we saw in spectral form factor. And moreover, you should also integrate over the overall energy of the system, because we don't have this state anymore, which is what fixed the energy to be something definite. Now you should integrate over the energy. And if you go through and play your path integral games, you can get all the factors of 2 pi to work out just right, so that you exactly get from the zero modes of this path integral the random matrix answer. Right? Yes, please.
So in the original Lagrangian, you said that there was a term that looked like a chemical potential. I mean, this, the D delta thing.
Yeah, this is like this is just the great Laplacian.
Oh, it's okay.
Yeah. So that's just the diffusion equation there. So this zero mode actually gives you random matrix theory. It predicts it. And then you can go and do the calculation in detail. I won't go through this in any way. Just to say you can do the full path integral, and you exactly reproduce the formula that we had previously from this return probabilities point of view. So we set out to explain not random matrix theory itself in this system, but just how the slow modes give way to random matrix theory. But what we came away with is actually a theory that predicts the random matrix behavior itself, as well as the corrections to it. And in fact, now we can do better. We can even go and compute systematic corrections to this, because diffusion is not an exact law of nature. There are fluctuations, nonlinear effects that you can include, and those can in principle modify the story I told you here. But now we have a systematic quantum field theory framework for dealing with that. But it's of a sort of exotic kind, where you need to do field theory on time loops. So it's a sort of different sort of beast than you're used to, but it's manageable, it's tractable, and you can extract a lot of physics from it. Okay, so I want to wrap up there. What I've shown you today, or tried to convey to you, give you a flavor at least, is that quantum chaos is this big, vague subject. When people say quantum chaos in a paper, they don't usually mean one specific thing. There's all these different manifestations of it, but we think, or at least I think, that they're mostly related to each other. And I tried here to explain how there are sharp connections between, for example, information scrambling and hydrodynamics. Information scrambling really justifies or explains how hydrodynamics emerges from this unitary system. And then how hydrodynamics itself predicts that the energy levels are random matrix-like, and lets you calculate corrections to that picture. So in this way, we make some sharp links between these different bubbles I drew at the start, and now we can say these things really seem to have to co-occur, and they're all part of one big story of quantum chaos. And along the way, I showed you a couple of very concrete things where you can apply this to actual experiments, or at least something that is experiment proximate. I showed you the NMR experiment in adamantane, and I also showed you how you can use this to calculate the transport properties of a strongly interacting system. And so that's kind of the directions we want to go next. We want to make, for example, these transport calculations more realistic. There are all kinds of experiments in 2D using quantum gases or real materials where we don't understand how to calculate. We don't understand the physics we're seeing. And maybe these ideas can be leveraged to give us a new approach to those problems. Of course, we'd like to understand how others of those bubbles are related to what I told you about here. For example, complexity growth, how does that figure into the story? And then there are even, of course, hopes for insights into black hole physics. For example, one thing that always puzzled me as a student was the horizon itself. It's this unidirectional thing. What does that mean? Like, how can that be there? how can it need to know the sort of whole future history of the universe to know where that is? But from this point of view, I would say there's sort of a candidate simple avatar of that, even in my simple spin chain, which is just the statement that if I drop some information into the system and I agree to never do anything very crazy, like reversing time, for as long as I want, then that information never comes out. So that's like a horizon there, and you might hope to turn that into a more sharp statement. For example, maybe there's some kind of phase transition in the accessibility of information, which is like a horizon but more general, right? So I think this is a very exciting field. I hope I conveyed to you a little bit of the excitement that we're feeling, and some of the theoretical and experimental ideas that go into this evolving subject. And thanks for your attention.
Thank you, Bram, for a nice talk. Let's see. We can have some questions. Okay. Start and we'll go over there.
On one of your very first slides where you show these computer simulations for the coupled spin system,
Yeah.
I was just wondering, so there is a characteristic RMS of this distribution which seems not to change with time. Now, there is no size, this one.
Yeah.
There is no size parameter here except for the number of spins. So what dictates the amplitudes of this fluctuation?
That's right. Yeah, we would think, roughly speaking, at late time, these are like random states in Hilbert space, and those would have some small fluctuation of order 1 over the square root of the Hilbert space size. So 2 to the, like this is 14 spins, I think, so 2 to the minus 7, roughly, which is actually pretty close to what you see there. There can be reasons why the fluctuations are bigger than that, but especially if you have conserved quantities, but that's the baseline expectation.
I was wondering if you could relate your emergence of hydrodynamics to sort of the standard criteria where the mean free path for scattering is small compared to the length scales that you're looking at.
Yeah, I think so, in the sense that, like if I go to this picture here, I want to kind of be on a scale large enough so that this operator looks sort of random-like in some precise sense, and the mean free path will control kind of how long it takes or how big it needs to be before that's the case. And so I think from that point of view, you'd see, yeah, let's say in a system where you had a sensible notion of mean free path and some like weakly interacting degrees of freedom, I think that would come in via this picture. But this is a sort of more general thing where you're going to ask, and this is something that you can ask precisely. Like in the numerics I showed, you can have a different version where you truncate operators that are more complicated than a certain size. And you probably need to keep the size bigger than the size of your mean free path to get the right answer. Otherwise, you're kind of introducing artificial dissipation that's not really there in the physical system. So we have some understanding of that, but it's incomplete.
Thanks.
Yeah.
I have a couple of questions, and I guess they're kind of related. So I guess the first question is actually related to this slide exactly. So just like kind of very simple-minded, like I just kind of see this as, I mean, you mentioned a light cone, but I almost kind of see this as like some sort of signal. Like you place a perturbation there, and it just kind of like some signal that gets released, like saying, oh, like this, there's like this perturbation here, and then there's like a signal that kind of, in some way, I just kind of think of it as like it communicates like kind of like information that there's like this perturbation here along one of these like spin channels. So I guess just kind of based on what you were saying throughout the talk on like if you have some sort of, you can measure these like deviations from like random matrix theory, for example, or like you can measure these systematic corrections. So is one way to think about it like you have these corrections, but you don't necessarily know what the perturbation or the initial perturbation that caused it was, so it's kind of some sort of like you have this like one, like a given correction or like set of corrections could correspond to like not just necessarily one perturbation, but like kind of like a set of or like multiple possibilities, and it's kind of like it's almost like probabilistic, like which perturbation in that set kind of caused.
Yeah. So you sort of mentioned two things there, I would say broadly. So let me comment on them in turn. So here, this really is like a speed effectively. And there's a speed which we define in the community called the butterfly speed. And you can actually argue very sharply that that speed is like an upper speed limit on how fast information can move. Now, this is like, it's not like a signal is propagating because it's like sending an electromagnetic wave through a plasma or something. It just dies away. The information is still there, but it's like in some complicated plasma fluctuations. So it's not like there's something coherent moving here. There's no peak. The peak will go away. But you can ask questions like, if I put some information in here, how big of a region do I need access to extract it out? And that's precisely characterized by this speed. Now, for your second question, or your second part about sort of many different initial conditions giving the same corrections, that's also an essential part of the story where you have this sort of forgetfulness or loss of memory, where no matter how you started out, you had this picture like this, where you get, in either case, more or less like the same noise at the end of the day, right? And so the noise, the statistical properties of the noise are predictable, but precisely what you get with any particular state is, of course, hard to say. So that's the sense in which, or that's one sense in which you have this kind of probabilistic emergence coming out.
Okay, sorry, I have one more question. If you could say, like, in one sentence, like, if you could define what is information in one sentence, what would you say?
Well, it's just a system that has many configurations it can be in.
So I guess the information would essentially correspond to like the system of
it's
configuration.
Just specifying, like what's the configuration of the system.
Okay.
Very crudely, I mean, one sentence level.
Next question over there.
So returning to that slide where you had a bunch of unitary kind of operations that you're doing, this reminds me very much of this recent work that was done by Ehud Altman and Sunwon Choi, where they introduced kind of random measurements and they noticed phase transitions, essentially, in information propagation. So here we have kind of the idea of like a Lee Robinson bound and kind of, some sort of emergent hydrodynamic picture.
Yep.
But in the case of something where information doesn't propagate in necessarily this one kind of canonical way, do you see kind of potential for the same emergent descriptions or maybe something that's kind of totally new?
Yeah, great question. So the question is about like if you sprinkle random measurements in here, what happens? And sort of very interestingly, if you make enough measurements just give you simple product states out. They destroy entanglement. So this makes entanglement, those destroy entanglement. And you can have a phase transition between a highly entangled state and a less entangled state. And in that case, there's a lot of extra complications because now you kind of have non-unitary evolution in some sense, like if you follow a particular trajectory, a particular set of measurement outcomes. So many of the same ideas apply, although they need to be modified. But like this information spreading is different. In some sense, you can if you can send the classical measurement results far away fast, you can spread the information faster than that cone I drew. So there's a lot of modifications that have to go on. And that's a very active, ongoing subject right now.
Okay, one quick question, and the last one is just a comment related to the quick question. The first quick question is, so if you now specify this to now a quantum hydrodynamics, like for example, a very simple superfluid situation where the field phi is now the order parameter of a superfluid, how would the calculation then apply there? So I take, instead of hydrodynamic, a superfluid.
Good, yeah. Well, you need to include like additional terms that deal with the superfluidity.
Right.
So we did this.
So lambda phi to the fourth interaction.
Yeah. We did this calculation in zero spatial dimensions, where there's no vortices, and in just the zero modes, like the Anderson tower of states. And there you can see how like the different symmetry sectors are initially decoupled, but then in finite size you restore the symmetry, you make cat states, and it goes to the full random matrix answer. And then with vortices, you just have to have these topological defects now So I think in principle I know how to do the calculation. I know how to write it down, but I haven't done it. And
Okay, good. That was a research question.
that would be a non-trivial paper.
Okay. So many years ago, Hivitsky and Das wrote a paper, it's actually re-emergent actually, where for certain types of matrix models, they showed a particular emergence of spatial dimensions from a theory it's just a n by n matrix theory. I guess it's a C is equal to 1 matrix theory. Yeah. But the question is, now I don't know how to make such theories random matrix models. That's a side issue. But I guess my question here is, it's more about a general question about what does quantum chaos signal? Does it signal something like quote unquote emergence in the sense of those matrix models?
I guess the picture I have, which I try to convey here, is that quantum chaos is actually something very generic, and apart from some special one-dimensional systems or systems with lots of disorder, it's kind of the de facto situation. And so in that sense, it shouldn't be able to tell us too much about the emergence of space-time by itself if we think of that as a more special thing that only occurs in some models. But maybe if we with some refined notion, like we ask that the system be as fast at scrambling as it can possibly be, or something like that, then we can start to understand what's special about gravity. But yeah, at this level, I would say it's not clear.
The last question. So quantum chaos being genetic, but maximal chaos is not genetic.
That's right. Yeah, maximal chaos is not generic.
What do you? How do you comment? You have a comment on that? How do we? Is that
well, I agree with your statement, and I would say there's a big ongoing body of work trying to understand what systems are maximally chaotic.
Yeah.
For example, in these spin chains, you don't even have exponent anymore. That goes away. You have some other kind of behavior. So even exponential growth is not generic, much less maximally exponential growth. So yeah, I think it's very open.
Yeah. Very good. With all those interesting questions and answers, let's thank Brian for
Thanks.
great presentation.